There is a substance so valuable that it was once used as currency, so essential that armies were paid in it, so important to human civilization that entire cities were built to control its supply and entire wars were fought to protect access to it. That substance is sitting in a small shaker on your kitchen table, and you probably haven't thought about it seriously in years. Salt, sodium chloride. The most ordinary mineral in most modern kitchens. The thing you're trying to eat less of because your doctor mentioned blood pressure. The thing you reach for automatically before you've even tasted the food. And the question of when humans started eating it, when in the vast timeline of human evolution and prehistory, salt went from irrelevant background mineral to civilizational necessity, turns out to be one of the most revealing questions in the entire history of the human species, because the answer is not a single moment in time. It is a process, a transformation, a complete restructuring of the human relationship with a specific molecule that unfolded over hundreds of thousands of years and that has left its marks in human biology, human economics, human politics, and the specific flavor preferences that feel to most people like simple personal taste, but are actually the expression of a deeply ancient biological need. Let's go through it properly. Start with the biology because before you can understand the history of human salt consumption, you need to understand why salt matters to the human body at a fundamental level. Sodium, the key element in sodium chloride, is essential for life, not helpful. Not beneficial at appropriate doses. Essential. The human body uses sodium to regulate fluid balance, to transmit nerve signals, to drive muscle contractions, to maintain blood pressure, and to enable the absorption of specific nutrients in the gut. Every time a neuron fires, sodium ions are moving. Every heartbeat involves sodium. Every muscle contraction depends on the electrochemical gradient that sodium helps establish across cell membranes. The body maintains sodium concentration in the blood within a very narrow range, approximately 135 to 145 millimoles per liter. Deviation below this range, called hyponatremia, produces confusion, seizures, and death if severe enough. Deviation above it, hypernatremia, produces dehydration, neurological damage, and death if uncorrected. The regulatory systems the body uses to maintain this range are elaborate, sensitive, and energetically expensive. The kidney monitors sodium concentration continuously and adjusts excretion rates accordingly. The hormonal systems of the renin-angiotensin-aldosterone axis are dedicated substantially to sodium management. The brain has dedicated sodium-sensing neurons. All of this physiological infrastructure exists because sodium availability in the ancestral environment was variable enough that robust regulatory systems were required. If sodium had always been abundantly available, evolution would not have needed to invest so heavily in conserving it. The existence of such elaborate conservation and regulation systems is itself evidence that getting enough sodium was, at some point, a genuine challenge. Now let's talk about the ancestral environment, because this is where the story begins and where most accounts of salt history skip directly to civilization without addressing what came before. The immediate ancestors of modern humans, the great apes, have low sodium requirements relative to body size. Chimpanzees and gorillas eat primarily plant-based diets, and many plants contain meaningful amounts of sodium. Fruit, leaves, stems, the foods that form the core of great ape diets, provide enough sodium to meet the relatively modest requirements of an animal that isn't sweating heavily or processing large amounts of protein. The transition to a more active, more carnivorous, more open-terrain lifestyle in the human lineage changed this equation. Hunting and gathering in hot environments produces significant sweating, and sweat contains sodium. Approximately 1 gram per liter of sweat in most individuals. An active hunter-gatherer sweating through a day of activity in a warm environment can lose several liters of sweat, representing several grams of sodium. This loss needs to be replaced. Meat, conveniently, contains sodium. Fresh blood contains significant sodium concentrations. Approximately 3 grams per liter, similar to the concentration in seawater. Organ meats contain sodium. The shift toward higher meat consumption in the human lineage was, among other things, a shift toward higher dietary sodium availability that partially offset the increased sodium losses from sweating. But here is the critical question that sets up everything that follows. Did early hunter-gatherers seek out salt specifically, the mineral in its pure or nearly pure form, or did they simply obtain adequate sodium through the foods they ate, the way great apes do, without any awareness of or interest in salt as a separate substance. The honest answer is that we don't know with certainty, because the direct evidence doesn't survive in the archaeological record the way bone tools and fire hearths do. Salt leaves no lasting physical trace at sites where it was merely consumed rather than processed. But the indirect evidence from physiology, from animal behavior, from the behavior of modern hunter-gatherer groups, and from the very early evidence of salt use that does survive, allows a coherent picture to emerge. Animals seek salt. This is so consistently observed across mammalian species that it is one of the most reliable generalizations in zoology. Ungulates travel significant distances to mineral licks, natural outcroppings of salt, and other minerals that animals lick to supplement their dietary mineral intake. Herbivores are more reliably found at mineral licks because plant-based diets are lower in sodium than animal-based diets, and the deficit must be supplemented. Carnivores are found at mineral licks less reliably. Their diet provides more sodium, but they appear there too. Early humans watching animals visit specific locations with regularity, and early humans were expert animal observers, would have eventually investigated those locations. They would have tasted the mineral that was drawing the animals. And sodium chloride is detectable by the human tongue at low concentrations, produces an immediate and rewarding flavor response, and meets a genuine physiological need. The discovery of salt as something worth seeking, separate from the food that contained it, was probably made many times in many places independently by groups following animal behavior patterns that led to natural salt sources. This is conjecture, but it is informed conjecture. The alternative, that early humans ignored salt licks that they watched animals seek out enthusiastically, and only discovered the value of salt after agriculture and civilization had developed, is considerably harder to believe. Now let's talk about what natural salt sources actually look like in the landscape, because this detail is almost always omitted from accounts of early salt use, and it matters for understanding how early humans would have encountered the mineral. Natural salt sources take several forms. Inland salt lakes and playas, dried lake beds, occur in arid and semi-arid regions across Africa, Asia, and the Americas. These are areas where water evaporates faster than it replenishes, leaving behind concentrated mineral deposits including sodium chloride at the surface. The Afar region of Ethiopia, which is also one of the most important regions for early human fossil finds, contains multiple significant salt deposits at the surface. Early hominins living in or moving through this region would have had regular contact with exposed salt minerals. Salt springs occur where underground water passes through salt-bearing geological formations and emerges at the surface with elevated sodium concentrations. These springs attract wildlife consistently and would have been recognizable to early humans as unusual water sources, saltier than typical water, drawing more animals than typical springs. The association between unusual-tasting water and high animal density at specific locations would have been a reliable pattern that any observant group would have noticed. Coastal environments provide another natural salt source through sea spray, tidal pools, and the bodies of marine organisms. Groups living near coastlines had access to sodium through multiple channels simultaneously: seafood with natural sodium content, seawater rinsed vegetation, and the direct experience of salt through marine environment contact. Coastal populations of early humans, which are thought to have been significant in the dispersal of modern humans out of Africa along coastlines, were probably never sodium deficient in the way that interior populations could be. The geographic distribution of natural salt sources therefore shaped the geography of sodium availability for early humans, with coastal and certain interior regions having reliable access and other interior regions having more variable access. This geographic variation is likely reflected in the variation in salt-seeking behavior and eventual salt production that developed differently in different parts of the world. Now, let's talk about something that almost never appears in histories of salt, but that the anthropological record makes surprisingly clear: the specific methods that traditional peoples without access to refined salt used to supplement their sodium intake, because these methods tell you a great deal about how early humans managed the same problem. Several traditional cultures in tropical rainforest environments, where natural salt sources are rare, and dietary sodium from plant foods is low, developed practices of burning specific plant species and consuming the ash. Certain plant ashes are rich in sodium and potassium, minerals that the plants concentrated from the soil during their growth. The deliberate burning of specific plants and consumption of the resulting ash as a condiment is documented in indigenous communities in Papua New Guinea, the Amazon basin, and parts of Central Africa. This practice is significant because it demonstrates that the drive to supplement dietary sodium was strong enough to produce significant behavioral innovation in the absence of direct salt sources. These communities didn't have access to mineral salt. They invented a salt equivalent from available materials. The biochemistry of what they were doing, consuming sodium-rich ash mixed with food, is functionally identical to salting food. Only the source differs. Other traditional communities have used specific plant species that concentrate sodium in their tissues as dietary sodium sources. The specific botanic knowledge required to identify which plants in a given environment are highest in sodium, and to use those plants preferentially in ways that supplement dietary sodium, represents a form of nutritional intelligence that has been documented but rarely discussed in the context of salt history. These practices represent the intermediate stage between purely obtaining sodium through diet, the hunter-gatherer baseline, and deliberately seeking, producing, and using mineral salt. They are the evidence that the behavioral drive towards sodium supplementation is ancient and persistent, expressed in whatever form the available environment allows. The earliest confirmed archaeological evidence of human salt use is ancient, though not as ancient as the probable period of initial discovery. At Lunca in Romania, archaeological evidence suggests salt production from brine springs, dating to approximately 6000 BCE, approximately 8,000 years ago. This is not the earliest evidence of salt use, but it is the earliest evidence of deliberate salt production, which is a more advanced stage of the relationship. By 6000 BCE, someone in what is now Romania had figured out not just that salt was valuable, but that naturally occurring brine, salt-saturated water, could be boiled to extract solid salt at scale. The implication of production is that demand existed that natural sources couldn't fully meet. Demand sufficient to justify the significant fuel and labor investment of boiling brine. You don't develop salt production technology unless you are already dependent on salt in quantities that passive collection from natural outcroppings can't provide. The transition to agriculture is the key inflection point in the human-salt relationship, and understanding why requires understanding something about how agriculture changed the human diet. Hunter-gatherer diets are high in animal products relative to agricultural diets. They are high in fruits, nuts, and tubers that contain meaningful sodium. They are also diets of considerable variety. Different foods eaten in different seasons, in different proportions, providing a range of nutrients in combinations that change continuously. The sodium content of a hunter-gatherer diet, while variable, appears to have been adequate for physiological needs through the food itself, supplemented by whatever salt was available from natural sources when it was encountered. Agriculture changed this dramatically. Agricultural diets are dominated by grain crops, wheat, rice, maize, millet, that are extremely low in sodium. Grain contains very little sodium. A person eating primarily grain has a dietary sodium intake that is a fraction of what a hunter-gatherer diet provided, while their physiological sodium requirements remain exactly the same. This is the salt gap that agriculture created. It is not a small gap. The difference between the sodium content of a grain-based agricultural diet and a varied hunter-gatherer diet can be several grams per day, a difference that has profound physiological consequences and that must be supplemented from an external source. Agriculture also increased population density and enabled the development of social complexity, trade networks, specialization, storage systems, eventually states and cities. All of these developments required preservation of food at scales that hunter-gatherer bands didn't, and salt is a preservative. Not because our ancestors figured out the chemistry of osmotic bacterial inhibition, they didn't need to understand the mechanism to observe the effect. Salted meat lasts longer than unsalted meat. Salted fish lasts longer than fresh fish. Salted vegetables can be stored through winter. Salt enabled the food storage that enabled the population densities that enabled civilization. These two functions, dietary supplementation and food preservation, drove salt from a pleasant mineral encountered occasionally in the landscape to one of the most strategically important substances in the ancient world. The transformation happened over several thousand years of agricultural development and is visible in the archaeological record as the density of salt production sites increases. The complexity of salt production technology grows, and the evidence of salt trade across significant distances multiplies. The Roman Empire's relationship with salt is the most commonly cited historical example, and it is cited often because it is striking. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Roman soldiers received a salarium, an allowance for salt, from which the English word salary derives. The Via Salaria, the Salt Road, was one of the oldest roads in Italy, predating Rome's imperial period and existing specifically to move salt from the salt pans at the mouth of the Tiber to the populations of the interior. The Roman salt trade was state-controlled, taxed, and strategically important in a way that reflects how central salt had become to the functioning of a large, grain-eating, food-preserving civilization. But Rome was not where this began. Salt trade routes in China date to at least 2700 BCE, where legendary accounts attribute salt production to an early mythological emperor. Salt production in the Sahara was sufficiently organized by the first millennium CE to drive trans-Saharan trade routes that connected sub-Saharan Africa to the Mediterranean world, routes along which salt from the Sahara's interior was traded weight for weight against gold from West Africa. Salt pans in the Yucatan were important enough to the Maya that their control was a significant factor in political geography. Salt springs in North America were fought over by indigenous nations before European contact. Every complex civilization independently converged on the recognition that salt was essential enough to organize production, control distribution, and tax consumption. This convergence across cultures with no contact with each other is not coincidence. It reflects the underlying biological reality that salt is physiologically required, that agricultural diets don't provide enough of it, and that whoever controls salt controls something people will pay essentially anything for. The economics of necessity are unusual. Salt is not a luxury good whose demand falls when price rises. It is a necessity whose demand is relatively inelastic. People will trade gold for salt because the alternative is dying of sodium deficiency or losing all their preserved food to bacterial spoilage. This inelasticity made salt the ideal tax base for pre-modern governments, and the ideal trade good for merchants. It is always needed, it is always worth something, and nobody can choose to stop using it. The British salt tax in India, the specific colonial policy that made salt expensive for a population that depended on it, was what Gandhi chose as the symbol and the target of his first major act of civil disobedience. The Salt March of 1930, in which Gandhi walked 240 miles to the sea to make salt in defiance of British law, was chosen precisely because salt was the most universally understood necessity. Everyone needed it. Everyone resented paying the British tax on it. The mineral on your kitchen table has been worth marching for. The French gabelle, the salt tax that was one of the most hated fiscal policies of the ancient regime, was a direct contributor to the social grievances that culminated in the French Revolution. The gabelle was not just a tax on a commodity, it was a tax on survival. Every French peasant eating grain-based food in a climate that didn't permit year-round foraging needed salt to preserve food for winter. Taxing salt was taxing the ability to eat. The rage it produced was proportionate to the biological necessity of what was being taxed. These political consequences of salt taxation are not coincidental. They follow directly from the biological reality that salt is not optional, cannot be substituted, and cannot be produced by most people without access to specific natural resources. The political economy of salt is the political economy of necessity. And necessity-based political economies produce the most intense conflicts when access is restricted, or when the cost of access is manipulated by those with control over supply.